Hi all, this is the introductory presentation of our project of implementing hardware optimized long short-term memory units on FPGA to improve the performance of RNA networks. So directly going to the problem description, long short-term memory elements are the main building blocks of modern RNA networks. So the RNA networks are being used especially in the use cases where you have a sequence of data points which are very correlated. So the RNN kind of networks are fully optimized to understand these correlations and predict based on that. So the so the main issue with the LSTM right now we have is that due to its complexity, most of the GPUs and CPUs are not fully optimized um, to predict in LSTMs. Uh, because of that, the framework like TensorFlow and PyTorch are doing lots of software improvements to mitigate that. And using FPGA, we plan to implement a native hardware level LSTM cells, and we expect it to have a better performance at very low cost. And from the other hand, the power consumption of FPGAs are very low compared to the CPUs and GPUs, and this might make more efficient to run the FPGA based LSTM cells at edge computing levels. So this is a reference architecture we came up to present in our project. So we have 7 LSTM units connected together, and each LSTM unit has 16 different hidden states. And as the input, we plan to provide an input vector with the size of 7, and as the output we plan to expect a single output. So this is more like we push a sequence into the network and we plan to predict the next particular output. So this is the design of a LSTM cell. So in a typical, like the vanilla LSTM cell have a few different gates. So the first gate is the forget gate, where the you have a sequence of data and you need to forget some data points. So in the forget gate you keep track of the things where you need to forget, and more especially the other gate is the memory gate. So the memory gate keep track of the things that you need to remember. So because of these two different gates, it's the LSTM cells are fully optimized to train with short sequences as well as the very long sequences. So as the output, it outputs two outputs: the cell state, it's a state of the LSTM cell, and HT is the output of the cell, so which can be used from the next layers. So it accepts previous cell states and previous outputs of the previous LSTM cells, and it expects the XT is the current input of the sequence for this particular LSTM cell. So, so in our project, we are planning to implement each and every gate of the LSTM using VHDL language. So we plan to implement the matrix multiplication units, and we plan to implement nonlinear activation like sigmoid and tanh, and we plan to integrate these multiplication of the floating numbers into vectors using matrix summation units, and we finally try to wire everything together to uh, get a one single package of LSTM unit. So this is the project plan and the allocations, and so the main challenge we right now have is like implementing floating point arithmetic on FPGAs. So the as the first target, we plan to implement floating point multiplication and adding units uh, using VHDL, and then we try to extend it to uh, matrix level multiplication and addition units. Then we try to implement floating point nonlinear functions like sigmoid and tanh, which are being used inside the LSTM cells, and we plan to implement them using some lookup tables. and then we try to wire all these things together to uh, build a single LSTM unit. And we have some weight matrices and some input save on text files, and we plan to test each and every LSTM cell to see whether it's getting the right output. So then finally what we are trying to do is we try to implement our reference architecture using the LSTM cells and try to predict the uh, defined set of inputs to see whether we are getting the right output. So that's the end of our short 5-minute introductory video. So thanks for listening.